explained to you the day before yesterday, and yesterday I explained to you the bosonic version of this higher spin CFT duality, and yesterday I already indicated what you should do in order to make it supersymmetric, and the idea for making it supersymmetric is so as to connect it with string theory. So I already explained this sort of briefly, and I don't really want to explain more about it. If you have questions, I'm happy to explain more. Now, these wolf space cosets, these theories that appear here, they have what's called large n equals to 4 superconformal symmetry. And for the moment, I don't want to explain this to you in detail because this is going to scare you a bit. But in about half an hour, I'll explain this in more detail to you because it will be important in another context. But for what I'm about to explain to you, you can just take large n equals to 4 superconformal algebra to mean that it has a Virasoro factor, 2 SU2 factors, and a U1 factor. I mean, these are SU2 affine Kac-Moody algebras. They basically come from the S3s. The S3 has an SU2 symmetry, so each S3 gives you an SU2. The AdS3 factor gives you Virasoro. The S1 gives you a U1. Then you have 4 supercharges, and it's a somewhat complicated algebra. Excuse me. And I'll promise you'll see it later in full glory, but don't hold your breath. So what's the picture you would have in mind for this higher spin CFT duality? So it has large n equals to 4 superconformal symmetry. So this suggests it should have something to do with string theory or higher spin theory on AdS3 cos S3 cos S3 cos S1, because the symmetries basically tells you what the background geometry wants to be. And what we've proposed, or what we've found, is an example of a duality between a higher spin theory based on the supersymmetric extension of this HS lambda algebra and these wolf space cosets, and that has been tested as well as the bosonic versions of this higher spin CFT. So this is sort of this is the left-hand side of this story. Now we want to connect this to string theory. So ideally, we would like to connect this to the string theory dual of the CFT dual of strings on AdS3 cos S3 cos S3 cos S1. Now unfortunately, nobody knows what the CFT dual of string theory in AdS3 cos S3 cos S3 cos S1 is. In fact, that's something I'm going to explain to you towards the end. We are currently working on that, and that will be the second half of this lecture. But what is known at present is what the CFT dual of this small n equals to 4 version of AdS3 is. Namely, if you look at AdS3 cos S3 cos T4, say, this theory is dual to a theory with small n equals to 4 superconformal symmetry. You see this is smaller than the large one. And it's smaller because it just has Virasoro SU2 4 supercharges. It doesn't have the second SU2 factor. And for that, there is a very convincing proposal for what the CFT dual is. This has been tested to death. This has been explored in all sorts of different ways, so there is enormously good evidence for the fact that the CFT dual of string theory in AdS3 cos S3 is the symmetric orbifold of T4. So what this is T4 to the n plus 1 divided by Sn plus 1, and you excuse hopefully why I denote this by n plus 1. This will become clear later on why this wants to be n plus 1 rather than n. Obviously, it's going to be the larger limit, so whether it's n plus 1 or n, nobody cares. But for purposes of presentation, it's useful to think of it. So what is this? This is the theory where you take n plus 1 copies of T4. T4 are 4 free bosons and 4 free fermions. You take n plus 1 copies, so the 4 bosons each have an additional index I, running from 1 to n plus 1. And then you write down all the things you can make from that are symmetric under the permutation group, in the same sense as the invariance that Sanjay Rangulan was describing yesterday. This describes really the untwisted sector of the symmetric orbifold, and then you have twisted sectors that correspond to the different conjugacy classes of the permutation. That's all you need to know in order to understand it. Now the problem is here, like always in life. I mean, you have one thing here that you understand, and you have one thing here you understand, but these are like apples and pears. You can't quite compare them. You understand the string theory dual for the case of AdS3 cos S3 cos T4, but unfortunately we have no idea what the higher spin theory dual of this background is. There is no good coset proposal. There is no sensible idea of what the higher spin theory should be on this side, and there is no sensible idea of what string theory should be on this side. So you seem to be stuck because you basically know two things, but you don't know them at the same point where you could. But if you're a physicist, then you may consider doing the following. You see, this is AdS3 cos S3 cos S3 cos S1. So suppose I take one of the radii of the S3 very, 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 very large. Then if I'm a physicist and I ignore all sorts of global properties of S3, I can say S3 very large is basically the same as R3. Okay, it's not quite true because there are winding modes, but let's ignore them. Just let's look at things that don't have any funny global properties. And R3 is essentially the same as T3. Again, as long as I don't worry about winding modes. So if I think about things that don't involve any winding, none of the non-trivial global topology, then you see these two things are not that different at all. Because if I take the radius of this very, very large, then this should approximate more or less the zero winding piece of that theory, the zero winding, zero momentum piece of that theory. And you see all the interesting things that have been tested here live in the zero winding, zero momentum piece. All the BPS states, for example, live in the zero winding, zero momentum piece of that T4.
Just to clarify, you have so many radii at your disposal?
Yeah, so very good question.
So they are related, they are supposed to be related?
Very good, very good. So here, I'll explain this later on in more detail. But there's a radius here and a radius here. You can pick arbitrarily. Once you've picked those, the radius of AdS3 is fixed. But you can choose these two radii independently. That's the two levels of the SU2 algebras that appear in the large n equals to 4 superconformal algebra. And you can pick them independently. But once you've picked them, the central charge, i.e. the radius of the AdS3 factor, is fixed.
And S1 size?
The S1 size goes along for the right. I mean, the S1 is also a free parameter, but it will not play any role in what we'll be doing. Maybe that's a bit worrying, but it doesn't. But it really doesn't also play a role here, because you look again. We are looking at a zero momentum, zero winding sector, so the momentum will not play a role. So what it suggests, if you are brave, is that what you should be doing, you should be looking at the limit where the radius of one of the 2 3 spheres goes to infinity, and what this corresponds in terms of this lambda parameter of h as lambda. So there's this lambda parameter. This lambda parameter goes to 0. This lambda parameter is basically n over n plus k plus 2. And taking the one of the spheres to infinity corresponds to k going to infinity. So that means you should take lambda goes to 0. So what this suggests is that in the lambda goes to 0 limit, this left-hand side sort of becomes comparable with the right-hand side. And then the old picture should emerge, that higher spin theory should be a subtheory of string theory. So what you would expect is that the higher spin theory in this limit is a piece of the string theory, and correspondingly the Wolf space cosets should be a subsector of the symmetric orbit. That's a prediction if you believe that higher spin theory is the leading Regge trajectory piece of string theory in the tensionless limit, you would believe that that's how it should be. But that is now a very testable prediction, because you see these Wolf space cosets we know as explicitly as we want. We have to take lambda goes to 0. We know what this means. This means taking the level to infinity. So we have a very clear picture of what this theory looks like in this limit, and then you can compare to the symmetric orbifold and see whether it fits or not. It either fits or it's not going to fit. So there is not much room for picking. So what do these Wolf space cosets look like? Well, don't be scared. So there are some funny cosets, but you see we're looking at them in the large level limit. So what happens to a Wessel-Witten model when you take the large level limit? So the Wessel-Witten model is the string theory on the group manifold, and the level is basically the size of the group. So when the size of the group becomes very, very large, this group manifold becomes flat, and basically what you're going to get is dimension as many free bosons as there are elements in the group, as the dimension of the group. So what happens is that SUN plus 2 level k becomes n plus 2 squared minus 1 free bosons in the limit k goes to infinity. SUN level k plus 2 becomes n squared minus 1 free bosons in the limit k goes to infinity. These are just the free fermions, and the U1 don't do much. So what you find is that if you look at this perturbative piece of the Wolf space coset, so these are precisely the degrees of freedom I was describing yesterday that correspond to the higher spin fields and the scalar degrees of freedom of the dual higher spin theory. What you can show is that they are equal to 4n plus 1 free bosons and 4n plus 1 free fermions, provided you restrict to the singlet sector under the group action UN. That's what comes out of this Wolf space analysis. I mean, you take this Wolf space cosets, you look at the perturbative piece of the spectrum, that corresponds to the higher spin fields and the scalar fields. You know precisely which representations of the Wolf space coset they are. You take the limit k goes to infinity, and the partition function is simply equal to the partition function of 4n plus 1 free boson, 4n plus 1 free fermions, provided you restrict to the UN singlet sector. And you see, this is also very plausible because this looks like Klebanov and Polyakov, or like a Zuzi version of Klebanov and Polyakov, because there what you would do is you would take the ON vector model, you would take n free fermions or n free bosons and make them invariant under SON or UN or whatever you feel. So this is, I have to explain to you how UN acts on this, but there's a very definite prescription which comes out of this Wolf's-Guest coset description in this limit K goes to infinity, and there's no freedom here. This is something you simply deduce given the structure of this cosets. So if you work this out, what you find is that these 4n+1 free bosons and free fermions transform in the following representation with respect to the UN. And I've also written down the representation with respect to the SU2 that's part of the small n equals to 4 superconformal algebra. So with respect to the UN, the bosons sit in 2 times the fundamental, 2 times the underfundamental, and 4 singlets. Then the fermions sit in 2 times the fundamental, 2 times the underfundamental, and 2 times the doublet. Where the 2 here, this 2 is the spin 2 representation of SU2. So they are sitting with respect to UN, they're sitting effectively in the same representation. You're just keeping track of the quantum numbers with respect to the SU2 of the small n equals to 4 superconformal algebra. So this is what this piece of the Wolf space coset looks like, the piece that corresponds to the perturbative degrees of freedom of the higher spin theory. The rest of the coset corresponds to these conical defect solutions. So from the point of view of this description, they would correspond to some twisted sectors with respect to UN, and that's where these holonomies that are associated to very small group elements come from. But let's just ignore them. Let's look at just the perturbative piece of the higher spin theory, the higher spin fields and the scalar fields, and there's just described by taking these free bosons and free fermions and looking at the UN singlet piece, and then you can just use what Sanjay told you yesterday and work out what states will survive. You have to pair the U with the U bar, the N with the N bar, and all the bilinears, and that produces for you all the invariants.
Just a small question. So yesterday we had this discussion about modular invariance and whether you have a complete set of fields.
Yes.
The coset theory by itself would be modular invariant.
Yes,
right?
but here I'm only looking at a piece of the coset theory, because again I'm only looking at those representations that are of the form 0 lambda. So this piece by itself is not modular invariant, but if I were to put in the rest, it would be modular invariant, but then I get also the twisted sectors with respect to UN.
But so apart from the conical defects, is there anything else? I mean, you seem to get everything. I mean, so then you know everything.
Yeah, you can know everything, but you see, I mean, the way you can think about this is as a UN orbifold. So I'm not sure whether you like this idea. I mean, normally you take orbifolds by discrete groups, but here you can think of this as an orbifold by a continuous group. So what this means in the untwisted sector, it means the obvious. Now the twisted sector is associated to conjugacy classes of the group. So what are the conjugacy classes of UN? Every group element is conjugate to an element in the Cartan torus. So the conjugacy classes are labeled by elements in the Cartan torus. So there's a whole family of twisted sectors, and the group elements sufficiently close to the identity that are part of the twisted sector. So you can make this pretty precise.
Continuous set of masses.
Yeah, and that's basically this. All of these additional conical defect solutions. They're parameterized by a family of elements, maybe one for each element of the Cartan torus of UN. So if you're happy to quantize that theory, go ahead. So now this looks very familiar to the very similar to the untwisted sector of the symmetric orbifold, which is what we expect to see from string theory. So what does the untwisted sector of the symmetric orbifold look like? Well, again, for reasons I'm looking at the n+1 copies of T4 divided by the symmetric group Sn+1. So these are 4 n+1 free bosons, and they're transformed in the defining representation of Sn+1. So they sit in the n+1 dimensional representation of Sn+1, but the n+1 dimensional representation of Sn+1 is not irreducible, because you see the n+1 dimensional representation of Sn+1 is the representation by an n+1 by n+1 matrix, where in each row and each column you have precisely 1, 1. So this is the n+1 dimensional representation of Sn+1, where you simply say the first vector goes to this, and the second vector goes to this, and so we write down the permutation. Now, as a representation of Sn+1, this representation is not irreducible, because if you let it act on the vector 1, 1, 1, 1, this vector obviously is invariant under the group action, because you see each one will precisely hit 1, 1 and will lead to 1, 1. Right? So this is clearly, this vector is mapped to itself under the whole group. So therefore, the n+1 dimensional representation of Sn+1 is not irreducible. It splits into the trivial representation corresponding to this vector, which is invariant. So n+1 is equal to 1, which is this vector, plus an n-dimensional representation, which you can define, if you wish, by going to a basis by going to an orthonormal basis where this is one basis vector and you choose the remaining basis vectors to be orthogonal to it, so you get an n plus n matrix action for Sn plus 1. So in terms of Young tableaus, this is this representation. This is the so-called standard representation. So you have n boxes in the first row and one box in the second row. This is the n-dimensional representation of Sn plus 1. Yes?
So can I just ask, what are these conical defects? Are they be interpreted as black holes?
Well, they are sort of like would-be black holes, except their mass is very, very small. So they are classical solutions that are very close in energy to your perturbative vacuum. Okay, so this n plus 1 free bosons transform in the standard representation and the trivial representation. And you see what this argument also tells you is that there is a natural embedding of Sn plus 1 into Un. Because what we are going to do is we take for every group element in Sn plus 1, we go through this procedure and we associate an n by n matrix to it. Right? This is the n by n matrix that acts in the standard representation. But this is a faithful representation because, I mean, you've just split off the trivial bit of this. I mean, this is the defining representation of Sn plus 1. There are no relations here. You split off the trivial bit. So this is a faithful representation of Sn plus 1, and therefore this gives you an embedding of Sn plus 1 into Un. So Sn plus 1 is a subgroup of Un. And therefore, any representation of Un you can interpret as a representation of Sn plus 1. Whenever you have a representation of a group that contains a smaller group, you can take the representation of the big group and think of it in terms of representations of the small group. So you can ask, what are the branching rules for the representation of Un going to the representations of Sn plus 1? So from the symmetric orbifold point of view, you have the action of Sn plus 1, and you have the action of Su2. This is how the free bosons and the free fermions transform. And now we can compare this to the action that we saw in the Wolf space coset. So remember there we had representations of Un, and there the bosons and the fermions transformed in the fundamental representation and the anti-fundamental representation of Un. So now you can ask, what happens to the fundamental representation of Un if I think of it as a representation of Sn plus 1? Now generically you would expect this to branch into lots of different irreducible representation because Un is a continuous group. Sn plus 1 is a tiny discrete group. So typically when you branch from an enormous group to a small group, a representation will break up in lots of different bits. But actually the fundamental representation of the Un just becomes the standard representation of Sn plus 1 under that branching. And the anti-fundamental does likewise, because you see Sn plus 1 is a real group, and therefore complex conjugation doesn't change the representation. You know that the fundamental and the anti-fundamental both branch down to the standard representation of Sn plus 1. But now compare what we have. From a Wolf space coset point of view, we have bosons transforming in the fundamental, anti-fundamental of Un, 4 singlets, and fermions in the anti-fundamental and fundamental and singlets. Whereas from the symmetric orbifold, we have 4 times the standard representation times 4 times the singlet, or 4 times the standard representation, 4 times the singlet. But under the embedding of Sn plus 1 into Un, this representation becomes this representation, and this representation becomes this representation, this representation becomes this representation, this becomes this representation. So the way these fields in the Wolf space coset transform under Un, if you think of them with respect to the Sn plus 1 subgroup, give you precisely the way they should transform from the viewpoint of the symmetric orbifold. And you see, this is not something you can, that's up to us. I mean, the Wolf space coset is whatever it is. The fields transform whatever way they transform. There is effectively canonical embedding of Sn plus 1 into Un, and it just comes out on the notes. So what this tells you is that the untwisted sector of the symmetric orbifold, these are all the states that are invariant under Sn plus 1. They contain all the states that are invariant under Un. Because you see, Un is a much bigger group than Sn plus 1. Being invariant under Un is much harder than being invariant under just Sn plus 1. So there are far fewer states that are invariant under Un relative to those that are invariant under Sn plus 1. So, but these states, as we've seen before, are precisely capturing the perturbative part of the higher spin theory on AdS3. So on the dual CFT side, the stuff that corresponds to the perturbative higher spin theory is naturally a subsector of the untwisted sector of the symmetric orbifold, which is the CFT or part of the CFT dual of string. So what this tells you is that the higher spin theory, the perturbative higher spin degrees of freedom are a subsector of the stringy degrees of freedom at the symmetric. And you see they close naturally on themselves, because if you take two things that are UN invariant and you multiply them together, you get something that's UN invariant. So they form not just a subspace, they really form a subalgebra inside this untwisted set. Because any two things that you multiply together that are UN invariant will remain UN invariant. So this gives you an example of this idea that the leading Regge trajectory really forms a closed subsector upon itself. So you don't see it directly in string theory, but you see the shadow world on the dual CFT. The shadow of the dual CFT of the higher spin theory is naturally a subsector of the dual CFT of the string theory, in precisely mirroring what you were expecting, namely that the higher spin theory would be a subsector of the string theory at this tension.
This is a technical point, but do I take the T4 theory in the Riemann sector or the Lebesgue sector?
This is in the Lebesgue sector, but there is also, you see, I mean, also on the wolf space coset, you have a Lebesgue in the Riemann sector, but the perturbative degrees of freedom. I mean, you know, the Riemann sector is 1/16 higher than the Lebesgue sector, and we have n fermions, and we are thinking of it in the large n limit. So the Riemann sector has energy of order n. So you always look at the Lebesgue sector.
Okay, very good. But in the NS sector, if I go to the Untwisted sector, I know, only the vacuum is the only massless state, and after that, I guess all the states have growing energy, right? There's no degeneracy.
Yes.
And on the higher spin side, you also need energies which are evenly spaced.
Right. Yeah. I mean, you get. I mean, here on this side, you just get these free fields, the Sn n+1 invariants, and on this side, you just get the free fields, but you just keep the UN invariants. I mean, it's just a subsector of the set of fields that you keep. I mean, inside the symmetric orbifold, we're looking at zero momentum, zero winding, otherwise it's not legal. So there it's just free fields, and you look at everything you can make out of the free fields that are Sn+1 invariant. And then here, you take the same set of free fields, and you just keep everything that's invariant under UN, where the Sn+1 action is embedded inside the UN. So if you demand it to be invariant under UN, in particular it's invariant under Sn+1, right? But there are many more states that are invariant under Sn+1 than just those that are invariant.
I'm just
under
wondering
UN.
what the states are, because let's say I have all in the
Okay,
Untwisted sector. What do I do to it to get, let's say, a spin S in the higher spins?
So maybe this will help. So the way you think about it is you have bosons. So A runs from 1 to n+1 and I runs from 1 to 2. So there are 4 bosons, 4 fermions, and the single particle generators of the symmetry algebra of the symmetric orbifold are all terms of that form. You take any P to be any derivative of anything made up from here, and you just sum over the common n+1 inputs. That's just one way of making it orbifold symmetry. That's basically the form of invariant theory that Sam Jain was just describing. So these are all the symmetry generators of the symmetric orbifold theory. So which ones are the higher spin generators? Which are the wolf space coset? Well, the wolf space coset generators are those that are just the bilinears, because you have to make them UN invariant. Well, there are 3 fermions, so there are 4 of these, and then you just keep the bilinears, because that's the only, the invariant theory tells you the only invariants are bilinears or product of bilinears. So the single particle generators of the higher spin theory are just the bilinear, and they're obviously a tiny piece of all of those, right? I mean, they're in particular included in those, but here you have many, many more, because you're not just having, you don't have to tie a U with a U bar, an N with an N bar, and particularly you don't just take 2, you can take 3 or 4 or 5 or 6. And in fact, the way you should think about it is you can decompose the symmetric orbifold symmetry with respect to this n equals to 4 superconformal symmetry, and you get a specific decomposition of which additional generators you need. And roughly speaking, the additional generators you need are those that involve higher powers of these P and P bar generations. And if you ignore whether they are P and P bar, the picture that emerges is that you should think of the quadratic terms. These are the original high spin fields as the leading Regge trajectory, and then the cubic terms are the first sub-leading Regge trajectory, the quartic terms are the second Regge trajectory, and so on. So these are additional Sn+1 singlets that are not UN invariant. And these are the additional generators that are symmetry generators of the symmetric orbifold, but not symmetry generator of the wolf space. Now the picture, I mean, why have I any right to say this? I have any right to say this because we've done this calculation where we switch on the string tension. So this is sitting at a specific point in the moduli space that's dual to the tensionless limit of string theory, because it has all of these symmetry currents. So what does it mean to switch on the string tension? Well, you should perturb this theory by switching on a specific exactly marginal operator of this symmetric orbifold CFT. And there is in particular, there's this two-cycle twisted sector operator that corresponds to switching on the tension of the dual string. So what you do is you calculate the anomalous dimensions of these various fields upon switching on this exactly marginal operator that moves you away from the symmetric orbifold. And then you have to, so these are these technicalities which we can discuss in more detail, but there's a specific way of calculating this. And when you do this, what you see is that the anomalous dimensions fall naturally in sort of bands. So that the quadratic terms, they seem to be the lowest mass state for a given spin. They all become massive when you switch on the tension because you are breaking all the symmetry. But the massive states are lighter than the cubic states, are lighter than the quartic states, are lighter than the quintic states. So that ties in with the picture that the quadratic states are the leading Regge trajectory, the cubic states are the first sub-leading Regge trajectory. So this gives a fairly explicit description of how you see the higher spin theory emerging inside the string theory, with the leading Regge trajectory being played by the higher spin fields themselves, and the additional generators that are symmetries at the symmetric orbifold corresponding to the sub-leading Regge trajectories of this string. Okay, that I hope that wasn't far too fast. How am I doing for time?
Half an hour.
Okay. So yeah, so maybe I'll skip over that.
So may I just understand a little bit better? So you need, so you're taking alpha prime to infinity in the, or you start with alpha prime to infinity in the symmetric orbifold.
Right. I mean that's
and then all the states become massless.
Yeah.
All the hashes.
Exactly. So that's our. I mean, obviously we are not literally taking alpha prime to infinity because nobody knows really how to relate string theory to the symmetric orbifold. You know the symmetric orbifold is one point in moduli space, and what we are proposing is that it's the dual of the tensionless point. Because at that point you have all of these massless mass fields. You have all of these conserved currents, so it looks very much like the dual of the tensionless point. Yeah.
And then they're not decoupled the Regge trajectories. They're all on top of each other.
They're all on top of each other because you have all of these symmetry generators corresponding to all of these higher powers. These are all correspond to massless degrees of freedom in the, massless higher spin fields from the point of the dual CFT because they have h bar equal to 0 and h equal to s.
But what you would like to do is somehow mod out all the other Regge trajectories. If you really wanted to get on the nose, then you want to just mod out all the other ones.
But you wouldn't
massless.
You wouldn't mod out. You wouldn't mod out. You would just concentrate on these. And this is what I was trying to say earlier. You see, the quadratic piece, the UN singlets, they form a subsector by themselves. So the higher spin P's are the things that are invariant under UN.
In the free theory.
In the free theory.
Okay, because otherwise they interact.
Yes, otherwise they interact. But in the free theory, they're the P's that are invariant under UN, so if you multiply them, they will close among themselves. So the leading Regge trajectory really forms a subsector that's closed among itself at the free point. Once you switch on the tension, obviously everything is going to start to mix. You can't hope to have a decoupled leading Regge trajectory behavior, but at the free point you see this very explicitly because you see two UN invariant states. If you multiply them, you get something UN invariant. So they form really a closed subsector, but the other things, the cubic and so on, they mix in all sorts of things.
Is the deformation that you turn on to make this, to decouple these different trajectories, is it some unique thing or anything that you turn on will actually...
Yeah, there aren't that many exactly marginal operators at a symmetric orbifold point. Well, there are a number, but it doesn't actually matter which one you pick. Each of them has this effect. So they all break this higher spin symmetry, and they all lead to this pattern of masses that look very much like separate Regge trajectories.
What are these extra points which don't lie on the line?
Yes, you see, it's a little bit complicated because the moment you start switching on the tension, all the different Regge trajectories start to mix. So, when you calculate these anomalous conformal dimensions, you have to work out something like this. So this is the perturbed two-point function of the two spin fields. Now, the moment you switch on the perturbation, everybody starts to mix with everybody. So this whole decomposition into leading the different Regge trajectories don't really decouple anymore the moment you switch on the tension, and therefore there is a. You see, this point morally used to be a quadratic term, and this point used to be a cubic term. But by the time they start you start perturbing them, there isn't one that you can think of as being quadratic and one of thinking of cubic anymore, because the real eigenstates are certain linear combinations.
Like mixing between single trace, multi-trace.
Exactly. I mean, everything starts mixing the moment you switch on the tension. So it's a little bit delicate, but what you see is that they try to fall into bands, and the states. I mean, for example, there are certain states that can't mix easily. So there you can, and certain states mix very little. I mean, so the logic here is that the diamonds are when you just do the perturbation within the family of the quadratic terms, and if you include the mixing. This state mix, and this moves up by this, and this moves down by this, and this moves up by this. So, but you still feel that you're morally right to think of this as being a quadratic term, and this as being a quartic term, because they are very close to the original quartic and very close to the original quadratic. But it obviously life becomes complicated. I mean, this separation in Regge trajectories will break down the moment you switch on the tension. That's what it should do, but you see sort of the traces that it really wants to lie on.
So this can be controlled, as you think. Right?
Yeah, I mean this is an honest conformal perturbation theory calculation. Obviously only first order, but this is something you can honestly calculate. But as you can also see, we stopped at spin 4 because this problem explodes very badly. I mean, everything starts to mix, and there are zillions of states, and we weren't smart enough to find a way of doing this. It would be interesting if one could do this a little bit more systematically to higher order. This is the poor man's way of doing it. You just diagonalize matrix elements and just brutally calculate it without being smart. So if you're smart, I think you should be able to push this further, but that's not what we've tried. Okay, so now, so the way you think about, one way to think about it is that the stringy algebra is really much bigger than the original higher spin algebra, and it tells you, I mean, there's a formula of which additional representation come in. But what's important is that what this means is that you can think of the stringy description as an extended chiral algebra relative to the original higher spin description. So you would think of this as a non-diagonal modular invariant from the Wolf space closure. And now one may hope that maybe one could use similar ideas in order to attack the problem of finding the CFT dual of AdS3 crosses 3 crosses 3 crosses 1, because we have the higher spin theory for these theories. These are these Wolf space cosets. And maybe we could start looking for extended chiral algebras that would mimic what happened at lambda equal to 0 in the T4 case. And that could give you a hint for what the dual CFT for AdS3 crosses 3 crosses 3 crosses 1 is. Now this is a long-term project, and in fact this has been a long-term project for a long while, and we got very, very stuck. But recently we got a bit unstuck. So I want to explain to you in which way we got unstuck. Now, one of the main problems of this large n equals to 4 superconformal symmetry is the fact that there is this large n equals to 4 algebra, which is called A gamma, and I'll explain it on the next slide. And there is the corresponding algebra of the supergravity background, which is just the wedge algebra of A gamma, and I'll also explain to you what that is. And part of the difficulty in this whole game is that the BPS bound of this algebra is stronger than the BPS bound of this algebra, and that has led to all sorts of obscure confusions. Maybe this is a point that doesn't interest you. Maybe I've gone off into some funny direction. But this is a problem that's been around for 15 years, and there are lots of confused papers about this problem. And there's a well-known paper by Gurkov, Martinek, Strominger, and Moore, where they explain on 80 pages why nothing works with AdS3 crosses 3 crosses 3 crosses 1. And this has basically been the state of the art since it was written 15 years ago. And what we've been trying to do is get unstuck at that point. So I want to explain to you in which way we got unstuck. So let me first explain to you in full glory what this large n equals to 4 algebra is.
I'm curious, interrupting. Is there some reality to D1 alpha?
There is certainly a duality, so alpha goes to 1 over alpha.
Reality.
Maybe also triality, I don't know.
Is it related to the triality which you talked about recently?
I doubt it, but maybe you can. So I'm only aware of a duality for D2 and alpha, because alpha and 1 over alpha are the same.
There is a paper by Elena Poletayeva from Texas about, I think, about reality.
Anyway, maybe you see what I'll do, and then we can. So this is the n equals to 4 algebra. So don't get scared. So let me talk you through this algebra. So this algebra has a U1 current, which is conveniently called U, and it's just a free boson, standard free boson commutation relations, and the supercharges and the fermions are related under the U1. Then it has 4 free fermions, which are these Qs, these are just free fermions, and the Q's appear in various funny places. Then it has two SU2 affine Kac-Moody algebras. They're called A plus minus I, so I runs from 1 to 3. They're just standard affine Kac-Moody algebras with levels K plus and K minus. And certain fields transform in certain ways under these SU2s. And then you have 4 supercharges, which are the G's. And the anticommutator of the G's gives you a central term, the stress energy tensor, and it couples to the 2 SU2s. And the way it couples to the SU2s is determined by a parameter gamma, or 1 minus gamma, which is the gamma in the A gamma name of the algebra. So this is the algebra on a superficial level. So it's characterized by 2 levels, which are K plus and K minus, and these are the radii of the 2 S3s. But the central charge, as Antal was saying earlier, the central charge is fixed by K plus and K minus. So K plus and K minus are the sizes of the 2 S3s, and the central charge is then fixed to be 6 K plus K minus over K plus plus K minus. That tells you you're free to choose the 2 S3s at will, but then the radius of the AdS3 factor is fixed by supersymmetry to take this. And this gamma parameter is just the ratio of K minus over K plus plus K minus. And in terms of D21 alpha, the alpha parameter is just the ratio of the 2 K minus over K plus. And because you can exchange the roles of the 2 SU2s, obviously alpha goes to 1 over alpha is the same.
All these parameters, they are just all real numbers or positive?
Well, so the case would really like to be positive integers, because there are levels of SU2 affine Kac-Moody algebras. So if you want to have unitary representations, the K plus and K minus should be non-negative integers. So this means that the radius of the 2 S3s is quantized there's a quantized flux through the S3. But everything else, so the C is then whatever it is. It's not going to be an integer, and gamma is whatever it is. So gamma needn't be an integer. Gamma is just the ratio of these 2 non-negative integers. So what are the highest rate representations or BPS representations of this algebra? Well, they're labeled by the conformal dimension, by the spins with respect to the 2 SU2s, and by the U1 eigenvalue. And you can work out what's the BPS bound. And the BPS bound, so this was done, this is all ancient history. So this is the form of the BPS bound. The conformal dimension has to be greater than this combination of the K's and the J's of this representation. So this is the A gamma algebra, the large n equals to 4 superconformal algebra. Now what you see in supergravity is not A gamma. In supergravity you see only the global part of it, which is the one that's generated by the L0, L plus minus 1, and it's just SL2. Then you have 4 supercharges with plus and minus a half, and you have the SU2, the 2 SU2 zeros. This is the algebra D21 alpha, and its highest rate representations are labeled by the conformal dimension, the eigenvalue under L0, and J plus and J minus are the spins with respect to the 2 SU2s. So obviously there is no U1 here, so the last quantum number is missing. That just isn't there inside the D2. So this is the D21 alpha. This is a very special Lie superalgebra. I think it's the only Lie superalgebra that has one free. It's a finite dimensional Lie superalgebra with one free parameter. Yes. And I think there's this classification of cuts, and there are all the standard ones, and then there's the one exceptional guy, and then it's D21 alpha. So as a string theorist, you believe this must play a role, because everything exceptional likes to come to us. Okay, so what's the BPS bound of D21 alpha? So you can also work this out. This was also worked out in the ancient history, and the BPS bound of D21 alpha is this form. I mean, there's obviously, if you compare this to the BPS bound of A gamma, this looks the same, right? The prefactor is the same, this factor is the same, this factor is the same. There's a U squared term here. Okay, the U squared term can't be there because there is no U. Fair enough. But there is this other term here, J plus minus J minus squared. That's a term that appears in A gamma, but it doesn't appear in D21 alpha. That just follows from the representation theory of these 2 algebras. I haven't done anything smart. I've just taken these algebras, imposed the BPS bound, and in one case I get this bound, in the other case I get this bound.
Do these appear at the same level, in the sense the null states when these are saturated, are they at the same level?
Well, not entirely, but because the A gamma has 3 fermions, but this is I mean, they have additional states, so if there are short representation, it contains 2 short representations of this type, but the main problem is that the BPS bound is not the same. So what does this mean, the fact that the BPS bound is not the same? So suppose you were to restrict, you looked at some, I mean, what this means is that the stringy BPS bound is stronger than the supergravity BPS bound. Because here this is this J plus minus J minus squared term, so this is strictly bigger than that, unless J plus is equal to J minus. And H has to be bigger than that if it's a representation of A gamma, and it has to be bigger than that if it's a representation of D2 alpha. But this leads to this obscure phenomenon that suppose you have some BPS state in supergravity where J plus and J minus are not equal. So then it will saturate the BPS bound of D21 alpha. Now suppose you switch on some quantum correction to go to string theory. Then suddenly this state has to acquire quantum corrections in order to even satisfy the BPS bound of A gamma, let alone saturate it. The state in supergravity that saturates the E21 alpha BPS bound will not saturate, will not even satisfy the BPS bound in string theory unless it acquires a quantum correction to account for this stupid correction term here. So this is bizarre. This is something people haven't seen anywhere before. You have these BPS states in supergravity, they are happily living along, and then the moment you think about quantizing the theory, they somehow suddenly have to jump up in energy in order to satisfy the BPS bound of the stringy algebra of A gamma. So, and the problem is more acute because the BPS spectrum was studied in this paper by Gaberdiel, Pascuccini, and Scandaris in '99, and they said there are BPS states for all combinations of J plus and J minus. In particular, there are supergravity BPS states where J plus is not equal to J minus, and therefore this phenomenon that I just described for you is not just some theoretical possibility, it must happen all the time for these BPS states that appear in supergravity. Because when you switch on and go to the quantum corrected string theory, somehow suddenly they all have to collectively acquire quantum corrections in order to even satisfy the BPS bound of the stringy algebra. Now the other thing that...
Explain again, what do you mean when you say that if you turn on some correction, you go to some string theory, and then what do you mean that you turn on some correction and becomes string theory?
Well, so this is supergravity bound. So you go to the limit where the string goes arbitrarily small. So that's alpha prime goes to 0, infinity, whatever. I don't remember. Now imagine switching on alpha prime a little bit. Then your theory is going to be a string theory, and therefore the dual CFT, the space-time spectrum, has to fall into representations of A gamma. So your state that had a specific combination of quantum numbers J plus, J minus, and H, and saturated the D21 alpha BPS bound, the moment you switch on, you make the string a little bit extended from a point-like object, suddenly H has to be bigger by that amount. Independent of how small you choose alpha prime.
You're saying that the parameter with which you're turning on the interaction doesn't enter into this.
Exactly. So suddenly, by making the string not being point-like anymore, suddenly you must acquire these quantum corrections to saturate this, to even satisfy the bound. I mean, it's not that you want to stay BPS, it's just saying that you want to stay consistent. I mean, you have to satisfy the inequality just to be consistent. And even that requires a non-trivial quantum correction if J plus is not equal to J minus. But according to this paper of the Gaberdiel, Pascuccini, and Scandaris, these states exist, so this happens all the time. But the other thing that was strange about this whole game was that so Gukov, Martinev, Moore, and Stromicher, they tried to find a dual CFT, and they tried everything they could think of, and they just couldn't find any CFT whose BPS spectrum looked remotely like the supergravity BPS spectrum of the Gaberdiel, Pascuccini, and Scandaris, and therefore they said, okay, so maybe the BPS states are not stable, maybe we can only allow to look at the index, so they invented an index with which is stable under perturbation, and then they looked at CFT duals that had the same index, but this index is really as bad as it gets. I think if you look at this index carefully, the only state that contributes to the index is the vacuum. And as a consequence, as a tool of identifying what the dual CFT is as useless as it goes. I mean, it just doesn't tell you anything because it's so poor information that it doesn't tie your hands anymore. So as a consequence, there was no way they could reach a conclusion of what the dual CFT is. So this is how this. I mean, this is the situation since 2004, and it has stayed like that since then. So what we've decided to do is to revisit this problem by studying the worldsheet description of string theory in this vacuum. And this is done together with a master student of mine, Lawrence Eberhardt, Rajesh Gopal and Wei Li. And I should really say that Lawrence is a very remarkable student. He started his master thesis 3 months ago, and he's really been the powerhouse in this collaboration. He's really learned all of that and done many of these calculations. It's very, very, very impressive. So what do I mean by worldsheet description of string theory? So what you do is you take the Wessel-Witten model corresponding to SL2R, SU2, SU2, and U1. That describes for you a string theory on AdS3, cosets3, cosets3, cos U1 with a pure Neveu-Schwarz flux, where these are the levels of the SL2 and the SU2 Wessel-Witten model. So a Wessel-Witten model corresponding to SU2 gives you a 3-sphere. So this is one 3, another 3-sphere, this is a circle, and that just gives you AdS3. So you just write down this worldsheet theory. We're not the first people to think of this. This was already studied in '99. And you can study what the critical string theory condition is, and that tells you that the level here is related to the levels here. So that 1 over k has to be equal to 1 over k plus 1 over k minus. This is just the condition that the total central charge is equal to 15. So then what you do is you just do your open Green-Schwarz-Witten on page 5, and you do covariant string theory. So you're just writing down the physical state condition, the positive Virasoro modes have to kill it, the positive supercharged modes have to kill it, and you have to write down the Mash-Shell condition. So what's the Mash-Shell condition? The Mash-Shell condition is, so you pick the spins of your ground states, these are the two SU2s, this is the SL2R, then this is the excitation number, so the excitation number plus this stuff must be equal to a half. That's the physical state condition, so that tells you the excitation number in terms of the representations that you choose for the ground states of these 3 Wessel-Witten models. Now the spacetime spectrum has a gamma symmetry at levels k plus minus. This was already shown in this paper by Elizur, Feynman, Givion, and Saba, and that goes back to the same technique that was used by Givion, Kutasov, and Seiberg earlier before. And you also know how to identify the spacetime Virasoro algebra from the worldsheet perspective. So the L0 of the spacetime spectrum is to be identified with the 3 mode of the SL2R Wessel-Witten. So basically, you have a worldsheet description. You can describe all the states of your theory, and you know how to look at them from the point of view of the spacetime CFT. So you can ask, which are the BPS states of the spacetime theory that are described by this worldsheet theory? I mean, it's a totally obvious question, and it could have been easily answered by these people then, but they didn't. I mean, somehow nobody cared to study the BPS spectrum of this background using this worldsheet description, although it's not really very hard. You'll see it in a moment. It's pretty easy to see what happens. So what we've done is we've looked systematically for the states with the smallest space-time conformal dimension for a given choice of spins. These are the states that are potentially the BPS states. So if you fix the spins, then you look at all the states of your space-time spectrum that have the smallest space-time conformal dimension for a given choice of spins. And then once you found the smallest one, you check whether it saturates the BPS bound or whether it doesn't. And because it's the smallest one, if it doesn't saturate the BPS bound, there is no BPS state in that sector because the conformal dimension would have to be small. So the first thing, so it's a little bit technical to do it, but the first thing you realize is that the excitation number wants to be equal to a half. You don't gain much by choosing higher excitation numbers. And in fact, you want this excitation number to lower the J0 eigenvalue of the SL3 factor, but you're not going to touch the SU2 quantum numbers. So when you choose n equals to a half, this a half cancels this a half, and this J gets shifted by 1, and then you can solve this equation for J as a function of J plus, and J minus is just inverting this quadratic equation. And when you do this, the answer is simply this. J is equal to minus a half plus a quarter times this. And then here it depends on k and k plus, and then we use the condition that k is a function of k plus and k minus, and then we can write it in this way. And we've also checked that, so if this is for the case where u is equal to 0, and we've looked at the unflowed spectrally sector. I mean, this AdS3 Wessel-Witten model a la Mandelstam and Oguri has this spectrally flowed sectors, but you can prove that the only BPS states can come from the unflowed sector, and in fact they can only come with u equal to 0. Non-zero u never buys you anything. So this is our result. We checked that this is the smallest j you can have for a given j plus and j minus in the space-time spectrum corresponding to this AdS3, cosets3, cosets3, cosets1 theory. So now you want to check whether this satisfies the BPS bound. Now the BPS bound should be satisfied automatically, but remember that space-time BPS bound secretly comes from unitarity. So in order to see this, you will have to impose the no-ghost theorem on SL2R. And what this means is you have to use the no-ghost condition for AdS3, which is that the ground state J0 must be less or equal than k plus 1 over 2. This is an old result. This is the reason why you need these spectrally flowed sectors. you have to restrict J0 to this bound in order for the space-time spectrum to be unitary. But if you use this condition, then you can prove with a little bit of effort that this value of J satisfies the BPS. So what you can check, it satisfies the BPS bound, and you can check when it's saturated, and you find it only saturates it for J plus equal to J minus. And again, when you put J plus equal to J minus, you see this simplifies very nicely, because this factor and this factor are the same. Then the K plus plus the K minus, this just cancel. This becomes a quarter plus J squared plus J. Then you can take the square root, and you just get the BPS bound. You see the BPS bound for J plus equal to J minus is very simple. You see this term goes away, this term is not there. If J plus is equal to J minus, you can just pull it out, and it becomes a very simple BPS. So what you find is that all states satisfy this inequality, and the BPS states are those that satisfy J plus equal to J minus. And this just comes out of an honest string theory analysis. No assumption, no nothing, right? We just take the pure Navier-Schwarz background, we analyze the space-time spectrum, we look at the states of smallest conformal dimension with respect to the space-time Virasoro algebra for a given J plus J minus, and we find the only BPS states arise for J plus J minus. So this is, excuse me, this is what string theory tells you. String theory at this point in moduli space has these BPS states. Now, if you stare at this equation and you know how string theory and supergravity are normally related, you realize that this equation is really a very natural equation from the point of view of supergravity. You see, if you use the usual relation between the mass of a scalar and the conformal dimension, and you take this equation and you write it in terms of a mass, then this equation is just that the mass squared divided by k, the mass in AdS divided by the radius of AdS, is equal to the Laplacian in the spherical harmonic J plus divided by the size of the sphere K plus the harmonic for the K minus divided by the K minus. So this just looks, I mean, this equation, reinterpreted correctly, looks like the standard supergravity equation, the most naive supergravity equation you would write down. So what this makes you believe is that this equation is probably also true in supergravity. I mean, it looks very much like it would want to be true in supergravity, because it looks just like the Laplacians on the spheres divided by the radii, giving you the mass on AdS3 divided by the radius. So this is our belief that this is the answer that you would get out of supergravity, but we felt we shouldn't just believe it, we should go down and actually do the supergravity calculation. So what we did is we repeated this exercise of Deger, Kaya, Seskin, Sandel, who had done it for AdS3 cross S3 cross T4. We've adjusted it to the case of AdS3 cross S3 cross S3 cross S1, and we've simply done the hard analysis, which de Boer hadn't done. Because you see, what de Boer had done, they hadn't actually done the honest supergravity analysis. They just assumed that everybody would be BPS, and they just used group theory to organize the spectrum in short representations. But they hadn't actually gone through the dirty analysis. Now this slide is deliberately black, because this is a black tunnel of long and hard calculation. I mean, this is a slide that looks deceptively simple, but this is a month of very hard work. I mean, certainly for somebody like me who has never done this is very hard, and you use Mathematica and you use everything that you can. We haven't done it for all the degrees of freedom. We've picked a scalar field in the Navier-Schwarz sector that's enough to see what happens to the multiplets, because each multiplet has one such state. And for each of them, we've diagonalized the Laplacian on AdS3, written down the Klein-Gordon equation, read off the mass, and what you find is you get exactly this. You get exactly this combination of the square roots appears, and it reproduces exactly what the string theory analysis told you it should reproduce. And therefore,
why the group theory that didn't work?
Well, because you see, the group theory told you that there were short multiplets, but actually these short multiplets always came in funny combinations that you could also have combined into a long multiplet. And what our calculation shows is that there weren't actually two short multiplets, but one long multiplet. But in terms of group theory, you can't tell. I mean, you could have fit them into short representations, but they assumed that everything would fit into short representations, and they formally fit into short representations, but actually they sit in long representations because their mass bound is not as it befits to sit in a short representation. So
is this the only example of such a situation?
Yes.
known so far.
Yes, that's the only. I mean, the Bohr didn't do this out of stupidity. I mean, for AdS3 cos S3 cos T4, AdS3 cos S3 cos K3, it just works exactly as you would believe. So he assumed it would be the same, and then he just used group theory to organize the spectrum in short representations. But actually, what happens is that in this case, it doesn't work. And probably in retrospect, the fact that the D21 alpha BPS bound and the A gamma BPS bound is sort of the reason why it couldn't. So you see, in particular, what this tells you is that also in supergravity, the only BPS states have J plus equal to J minus. Because you see, it's the same mass formula as for string theory, and therefore the A gamma bound is stronger than the D21 alpha bound. They satisfy the A gamma bound. They only saturate the A gamma bound for J plus is equal to minus. But at J plus equal to J minus, the A gamma bound and the D21 alpha bound agree. So that's where they also saturate the D21 alpha. So what this shows you is that the only BPS states in supergravity arise for J plus equal to J minus, and all the other ones, they automatically already satisfy the A gamma bound. So that there's no need for any quantum correction because the actual masses that these states have, they satisfy the A gamma bound, even at tree level in string. I mean, they're not BPS therefore, because the A gamma bound is stronger than the D21 alpha bound, and they're saturating neither. But in particular, they're still satisfying the D21 alpha bound. So when you make the string tension, you make the string a little bit longer, nothing specific has to happen to the conformal dimensions because they're anyway already above the bound where they have to be. So this removes this obscure problem of these funny quantum corrections. The simple reason being that there are no BPS states in supergravity for which this phenomenon would have to appear. Those states where it would have to appear aren't actually BPS even in supergravity. And in retrospect, I mean, once you see it, you say, how did it, I mean, it probably had to be that way. How could it ever have been otherwise? But that was the confusion that has been around for 10 years or so. So this resolves this mysterious problem, namely of these funny quantum corrections. But it also means that in terms of trying to search for the CFT dual, you may now try again to match just directly the BPS spectrum. Because you see the BPS spectrum in string theory, the BPS spectrum in supergravity are just on the nose the same. And there's a companion paper written by Regge, Torrielli, Olsen-Sachs, Stefanski, Sfondrini. They have used integrable techniques to study the BPS spectrum at some other point in moduli space, and they also see the same BPS spectrum. So the evidence is that the BPS spectrum is actually the same everywhere in moduli space, and therefore you can, in order to identify the dual CFT, you don't have to go down to this horrible route of just using the index. You can just take the BPS spectrum by itself and look for a dual CFT that has exactly that BPS spectrum, not just the index. And that obviously turns this into a much sharper problem again. A problem where you have a chance to find the CFT dual, because now you have a much sharper constraint of what the CFT dual has to do. So this is what we are currently working on. And what we want to do is we want to use the higher spin theory as a guide in order to help us find the CFT dual, using the inspiration that we have from the T4 case. Because you see there, the stringy algebra was an extension of this W infinity algebra. So again, here we hope, at least for the point where the two 3 spheres have the same size, that the stringy algebra is an extension of this W infinity algebra at lambda equals to 1/2. And it looks pretty promising, but we haven't quite sorted it out yet. So I don't want to say any more, but we believe that that is actually, I mean, now that the BPS, I mean, what has been vexing us for a long time is that the BPS spectrum of supergravity looked so totally different. But now that this problem is gone, I think we have a very realistic chance of finding the CFT dual, at least at that point in moduli space, and then hopefully for all the backgrounds of AdS3, cosets3, cosets3, cosets3. Okay, so I think my time is essentially up, and this is
Any questions? Well, if not, we'll reconvene after tea, so it's next speaker again.